This video is brought to you by Hygromo Chalk. Use code TPSA 10% off to get a discount.
Hello, my name is Thomas, and in this video series I'd like to give you an introduction to the mathematical theory of general relativity. So, or GR as I will often refer to it as. Okay, so what is general relativity? Well, general relativity is a theory of gravity. Specifically, it expands upon Newtonian gravity to incorporate relativistic phenomena. General relativity was discovered by Albert Einstein in the early 1900s after he developed his theory of special relativity. I will assume the viewer has at least some prerequisite knowledge of special relativity, but other than that, the mathematics and everything else will be pretty self-contained. Before we begin, I'd like to read a quote from the mathematician and theoretical physicist Edward Witten. So in an interview, he was asked, was general relativity considered popular or interesting at Princeton at the time you were a graduate student? To which Witten replies, well, I was certainly interested in it. I learned general relativity in a very excited period of about 10 days in the book of Steve Weinberg. This is a pretty remarkable quote. As he said, he learned general relativity in about 10 days. So what I'd like to do with this lecture series is to try capture this excited feeling of learning general relativity for the first time that Ed Witten has obviously experienced, and I myself experienced over much longer time spans than 10 days. And so yeah, that's what I'd like to do. Before I get started, I'd like to recommend some further reading and stuff like that. So the standard Candle textbook on general relativity is Sean Carroll's Spacetime and Geometry. He also has some lecture notes, which are a little less formal, which are also very good. There is also Brian Dolan, who's an Irish professor, emeritus of Maynooth and Dublin Institute for Advanced Studies. His book on Einstein's General Theory of Relativity is also a very, very good book. But if you want more mathematical or rigorous textbooks, there's the books of Robert Wald and Stephen Weinberg, as Edwin mentioned. I will also have lecture notes going over the material covered, which I'll also link. Okay, so to start, to call in Newtonian gravity, things are described by forces. So we have that Newton's law for gravity. The general picture is we have some bigger mass m surrounded and orbited by a smaller mass small m, and the force equation takes this form. Okay, so what I'd like to do, so from the get-go, this type of theory has conflict with special relativity. In Newtonian gravity, forces act instantly. No matter how far away these two masses are separated, the force on one exerts on the other is instantaneous. Now, from special relativity, we know that information can only travel at maximum the speed of light. So this type of theory must be an approximation to something else. That's kind of clearly the motivation for needing something like GR. This force equation, you may have noticed throughout your time studying physics, is very similar to another equation. So if we pull this one at grav, that is the force, the Coulomb force. So the force experienced by two charges will look something like this. So if we have two charges, Q1 and Q2, then the force between them is and also an inverse square law. So this similarity between electromagnetism and gravity is not seen in our everyday life. Gravity to us is very different. It governs the motion of planets and bodies, whereas electromagnetism is what's stopping the chalk falling through my hand. So despite this very similarly. Why are they so different? That comes down to two things. The first is this minus sign. This minus sign here means that if two masses have the same charge, then they will attract each other. So it's always an attractive force. And then if you pair this with the fact that there are no negative masses, this means that gravity is accumulative, meaning there are no, in electrostatics, you might have some like shielding-like effects, where if you have positive and negative charges, they can cancel each other out, whereas gravity will only add up. That's why on large scales, you only really see gravity. You don't see any sort of electromagnetism. Okay. The other thing is if you compare the forces, they kind of have two coupling constants. This one is for electromagnetism, and then this one is for gravity. If you actually compare these, you take like the magnitude of gravity over magnitude of the Coulomb force. This is a very small number, on the order of 10 to the minus 36. So the force of Coulomb force is way stronger than the force of gravity. The two other forces we have in nature, weak and strong, are both in. When I say strong, I refer to like between the force between protons and neutrons. These two forces are mediated by massive force carriers, being like the W and Z bosons for the weak force and pions for the strong force. Because they have massive force carriers, the force equation for them will contain a Yukawa-like term, meaning there's an exponential of or over some characteristic scale here. And what that means is these fall off way faster. So on large scales, you won't see any stronger force because this falls off way faster. Okay, so with that, with our talk of scales, and I have said that general relativity is a theory, a relativistic theory, we might want to know at what scale do objects become relativistic in regards to gravity. So to develop this fully, we'll obviously need to go through the whole theory itself, but we can get an idea for what this scale might be if we just analyze what constants do we think will be involved. So if I have mass m, as I said before, well then its mass might play a factor into what this scale is. The coupling constant for gravity, g, will also probably come into effect. And then since I'm asking when it becomes relativistic, another quantity might be involved is the speed of light, c. So with these, we can mess around with them and we can form a length scale. We can actually get a radius equal to, if I get it, and I get multiply g by m and divide by c squared. Well, this is actually has units length. So for an object of mass m, this kind of forms a length scale. And if I arbitrarily just divide by a factor of 2 for now, we can actually recognize this as you may have seen before, the Schwarzschild radius. So now you can derive this in another kind of naive way by making the escape velocity for an object leaving a body of mass m to become the speed of light. You'll actually get this exact same answer, but that is actually more of a coincidence than actually having something to do with that black hole or anything. Okay, so the Schwarzschild radius is, you haven't heard it before, it's, well, we'll come to it later, but so this is just some length scale at which objects become relativistic. So then we can check some objects that we know, like let's say Earth. So the Earth has a radius of about 10 to the 6 meters. So is it relativistic? Well, we can check its Schwarzschild radius. And its Schwarzschild radius is actually about 10 to the minus 3 meters. So it's about a millimeter. So the gravitational force at a radius or depends on the total mass enclosed in the region of, or in the volume of radius of a sphere of radius r. So if we were to get to Earth and squeeze it down to 10 to the minus 3 meters, then that object, Earth, would become relativistic. But it is far, far, far bigger than a millimeter, as you well know, so it's not relativistic. We also have things like the proton. The radius of proton is about 10 to the minus 15 meters. So we might think this has more chance of being closer to its Schwarzschild radius. But actually, if you check it, the Schwarzschild radius of a proton is actually about 10 to the minus 57 meters. So it's far, far away. Now, there may be some, so you can then think of some other particles like the electron, which in the standard model is a point particle, and then ask questions about whether that is smaller than its Schwarzschild radius. And yeah, we don't really know the answer to that sort of question. Okay, so the first step towards general relativity is to treat gravity as a field. So you may have seen in electromagnetism, it was actually the English physicist Michael Faraday, who was the first to abstract Coulomb's law to containing a field. So he said instead of having just forces between two charges, he said a single charge, so charge Q1 generates an electric field given by this equation. So this is a vector field, meaning at each point in space there is these vector lines, and it just looks like this. So that's that r squared. All right, and then he said any other charge Q2 in this field experiences a force Q2 times the electric field. So then we can do some things. Because this original charge Q1 is just static, it's just sitting there, the electric field isn't going to contain any energy in a sense. So that means it'll be conservative. A conservative field. You may have seen that conservative force fields have the property that the curl, that's nabla cross F, will be 0. So what this means from this equation is that nabla cross E is 0. Right? This is like one of the Maxwell's equations when there's no magnetic field. Okay, so with this, we can use a mathematical fact that the curl of the gradient of any scalar field, if I have some gradient of a scalar field phi, then the curl of that will always be 0. It's just a mathematical fact, the way with these, how these line up. So what this implies, since we have nabla cross E is 0, these two imply that we can write E as the gradient of some scalar field. I'm just going to put a minus there for convenience. Okay, we can then use Gauss's law. So Gauss's law tells us if we have some charge Q, then any surface surrounding this charge, the electric flux through this, which is given by the divergence of E, will be equal to the charge, will be proportional to the charge density. So the amount of charge contained in that region, which will be given by rho, and the constant proportionality is epsilon naught. This gives us the equation from this that minus nabla squared phi is equal to rho over epsilon naught. Okay, so that's kind of what's happening in electrostatics. Okay, now what I'd like to do is do the same thing for gravity. So I'm just going to rub this out. So what I can do is I can write the same thing. So I know I have a force law for gravity. So I can write down that a mass m generates a gravitational field G, which is equal to G big M, so this is a big M, over R squared. okay? And then I can do the same thing. And then the force on a charge of mass smaller m will look like this, F equals mg. And now the gravitational force, if the mass is just sitting there, it's not moving, also it's not going to be providing any energy. So this force is also conservative. So we also have that nav Laplace g is equal to 0 by the same logic we had before. And so again, we can write g as minus the gradient of some field phi. And this leads to, now, this Gauss's law, what we did for this, is equally applicable to gravity. We can say that the divergence of this field G is proportional to the charge density, and in this case, I think the constant proportionality is 4 pi G times the mass density in this case. So then we get the equation that looks like this. So this is kind of a Maxwell-like equation for the gravitational field. And this will become very, very useful later when we want to constrict GR, our theory of GR, such that in the classical limit, in the limit of when we're getting away from non-relativistic phenomena, we want to return to what we experienced in Newton's force and 1 over r squared, then this is how we will make contact with the classical theory, is this field setup. Okay, so Einstein and many philosophers of physics like to categorize physical theories into two types. There are constructive theories and principal theories. So the former, constructive theories, are theories that start out with a specific model used to describe some phenomena. This is like, for example, electromagnetism or thermodynamics. That's kind of how they built. You start with a model that describes phenomena. Now, principal theories are a little different. They start out with principles and then seek to derive as many things as they can from these principles before they come in contact with any model or anything like that. So special relativity and general relativity are both principal theories. They start out with principles. So what are the principles of general relativity? Well, the first one is what's called the equivalence principle. Okay. So what does this say? So we've been looking at gravity and electromagnetism. So, but why do we need, so general relativity, very weird special theory. Why, we've been seeing how gravity and electromagnetism are so similar, apart from a few small differences. Why do we need such a radical theory as general relativity to describe gravity? Well, we've seen already that the force force mass m experienced in the gravitational field will look like this. Now, if we just deal with the simplest case where, let's just say gravity is pointing down, and we'll just deal with the magnitude. So F equals mg. Now, Newton's laws tell us that force, a massive particle, will experience force F is equal to ma times its acceleration. Well, the keen viewer will use these equations and go, okay, well then we can immediately say that a is equal to g. The acceleration experience is exactly the value of the gravitational field. Now, we cannot say this in electromagnetism. In electromagnetism, F is equal to Q times the electric field. So this Q, the charge here in electromagnetism, is not the same as the inertial mass. So gravity is very special in that the gravitational charge is the exact same as the resistance you have to motion. So this is a very special thing, and it is one of the postulates, in a sense, of GR. So there are many theories that predict that this is not the case, that the inertial mass and gravitational charge mass are different. But the best experiments we have, I think the French satellite microscope has measured this up to sensitivity about 10 to the minus 15. So we've measured this pretty strong, that the gravitational mass and the inertial mass are the same. So the equivalence principle is kind of split into two parts. First is the weak equivalence principle. So what this says is that any object not bound by gravitational forces, so like me and you, we're bound by electrostatic forces. For any object bound by non-gravitational forces, their inertial mass will be the same as the gravitational charge mass. The strong equivalence principle is kind of the same, except it extends it to say that any gravitationally bound object, so something like the moon, has its inertial mass the same. This strong equivalent principle, the weak one holds in theories other than general relativity, but it is generally thought that the strong equivalent principle is only holds in general relativity. Okay, so what are the physical consequences of the equivalence principle? Well, what it says is that if you, let's say you are on the Earth in a box and you drop a ball, here you are, drop a ball, it's going to go like this. Equivalently, let's say you're in the middle of space with no gravity around and you're in a rocket ship and that rocket is accelerating. And on this rocket ship, you're standing there, you drop a ball. If your rocket's accelerating the same, at the same magnitude that the force of gravity is on Earth, then you'll see the exact same behavior. The ball will drop in the exact same way. What Einstein says is that if you were in a box in here, you would not be able to tell which of these scenarios you were in based on gravity. So what Einstein says is that these are essentially the same. But if these are the same, then it must also be true that if you stop your acceleration, now you're experiencing nothing, you're just sitting there floating through space. Well, that should be the same as if you go up to a very tall building and jump off in the box. So what I'm saying is, when you are in free fall in the gravitational field, it is the same as when you are stationary in free space. So this is very different to how we usually think about things. We think of being stationary when we are standing on Earth, but now we have to think about, well, that's actually when we're accelerating, and it's when we're in free fall that we are in what's called an inertial frame. All right, so this is how Einstein thought about these things. Okay, what this implies is really weird, because in a gravitational field, to be inertial means to move, but we're mainly in flat space. We're very much used to being stationary, meaning you are either literally at rest or moving at a constant velocity. So when you move at a constant velocity or when you're at rest, you move on straight lines. You don't go on curves things. But when you're in a gravitational field, what now was straight lines is now curved. It can be any sort of weird curved trajectory. So what Einstein took this to mean is that in the presence of a gravitational field, space itself is curved. Now, Einstein had just formulated his theory of special relativity, so he knew that space and time were intimately linked. So how he actually formulated this was not as a curvature of space, but a curvature of space and time, what's commonly referred to as spacetime. Okay, so when Einstein came to this problem, he realized he needed to mathematically formulate how curved spaces work. So this is quite daunting if you're a physicist. You're going to invent some new math. But he was very fortunate that mathematicians had actually been studying this for many, many years. There are many ways of describing curvature. You may have seen one of the most popular one is if I have a curved surface. So like this board is flat. So the angles of any triangle will add up to 180 degrees. But if it was curved and I drew the same triangle, these angles would change. If it was to come out of the screen or out of the board, you would see these angles would be bigger if it was kind of concave or less if it was convex and so on. The problem with this is curvature. This curvature coming out of the board is kind of embedding the whole board into a higher dimensional space and then putting the curvature. Now, as far as we know, our 3D or four-dimensional world, if you include time, is not embedded in some higher dimensional world. So we can't really have the curvature pushing into some other dimension. What we instead have is some intrinsic curvature. And what mathematicians found the best way to describe this is if you know the distance between any 2 points in your space, then you can completely describe the curvature. And a nice way to do that is to say, if I know the distance between any two infinitesimal points, then I can do integration to get the distance between any two finite points, and I can get the distance between any 2 points in the space. And that will completely characterize the curvature. So this type of this area of mathematics is known as differential geometry, and is quite important if you want to study your formulae. But in the next lecture, I'll introduce you to just enough so that we can proceed and do all sorts of fun stuff.